In Part 2 of Lecture 9, we discuss demand paging. Demand paging is the most popular form of virtual memory system. It is so called because we load pages only when there is a demand for them. This means that we do not predict the pages that we will need. We wait for the situation to occur when we need the page in question. This keeps down the number of pages that are actually in memory at any given time. It also requires that we know which pages in memory are valid and which pages are not valid. By this I mean which pages are actually in memory and which ones are not. And it means that the hardware must be able to support this. If the hardware cannot distinguish between resident and non-resident pages, we cannot implement demand paging on that system. As you have already seen, and will continue to see, the hardware determines to a very large extent what methods of memory management and virtual memory are available on a particular computer. Lastly, it is important to remember that until we have a page fault, and as long as we are accessing only those pages that are in physical memory, everything works the same as what we have already seen. How does the operating system handle page faults? It's a good question and an important one. The whole process begins with an instruction that accesses a page of memory. When that reference turns out to be a page not in physical memory, the operating system is signaled, as you see in this slide. Once the operating system determines the nature of the interrupt, it begins the process of handling a page fault. By the way, this will also happen if the next instruction to be executed happens to be in a different page of memory that has not yet been loaded. The next step involves finding the page on backing store. Once it is located, the page will be loaded into a free frame of physical memory. All will go well as long as there is a free frame available for it. If not, well, then we will have to determine which page is going to be swapped out. In either case, once we find a free frame, we load the requested page into it. After the page is loaded into physical memory, we have to update the page table to show that the page is not invalid and that it is in a particular frame of physical memory. After the page table is updated, the operating system can restore the process and continue by executing the instruction where it left off. The question that really needs answering is how many pages does a process need in memory at a time? Obviously, the absolute minimum would be the number of pages that are referenced by a single instruction. But that can be more pages than you would think. The worst case that you are likely to see is a 3-operand instruction. Although this is not too common, the VAX family of mini-computers did include a series of 3-operand instructions. This requires 4 pages in memory, 1 for the instruction and 1 each for the operands. The IBM 360 and 370 families of mainframes included an instruction MVC, move characters, which could move up to 255 characters in one shot. That requires at least 3 pages to be resident in memory, 1 for the instruction, and 2 for the source of the string and its destination. But what if either the source of the string or its destination, or both, straddles a page border? Then we might end up needing 5 pages. The VAX offers a similar example of how high our memory requirements might be. The VAX computer allows up to 2 degrees of indirect addressing. We might have to look in a register to get the address at which we find the operand's address. If we do this in a 3-operand instruction, that might bring our requirements up to 7 pages, and that's for 1 instruction. Fortunately, these are the worst cases, and even if they do occur, the odds are very good that these pages will be used by previous instructions or subsequent instructions. This will limit the number of pages that we might need over a limited stretch of code. Demand paging is a sort of good news, bad news scenario. The good news is that we can have larger programs. More programs fit into the same area of physical memory. The bad news is that the system will run slower overall with lower throughput, largely because of the disk operations caused by demand paging. The effective time that it takes to execute an instruction is the probability of no page faults times the machine access rate plus the page fault frequency times the time it takes to handle a page fault. If P is the page fault probability, 1 minus P is the probability of no page fault. Also, since it takes so much longer to handle a page fault than to execute an instruction already in memory, the second term becomes P times T sub PF. The largest term by far is the time that we will spend processing page faults. This makes it quite clear that any change in the probability of a page fault will have an extremely significant effect on the effective time of executing instructions.